Inside the 200-foot towers that refine our modern world, the stakes are incredibly high. A single hour of unplanned downtime can cost $1 million, with a production loss rate of $15,000 per minute. These 1,000-ton titans are the heart of chemical processing, where even a microscopic thermodynamic imbalance can trigger total mechanical destruction. These structures are marvels of engineering. The C3 splitter capstone stands 85 meters tall with a diameter of 6.5 meters, processing 120 metric tons of hydrocarbon mixture every hour. Its internal architecture features 180 high-performance stages, utilizing sieve and valve trays for stripping and structured packing for rectification. Engineering inside these towers is like managing a rainstorm within a hurricane. With a relative volatility of approximately 1.12, the boiling points are incredibly close. Engineers must perfectly balance the downward liquid flow and upward vapor thrust to separate these chemicals without blowing the liquid back up the column. We map this process using thermodynamic logic. The extremely tight gap between the operating line and the equilibrium curve dictates that exactly 180 physical stages are required to reach 99.5% propylene purity, with a critical reflux ratio of 11.5. The column's internal anatomy dictates its thermodynamic function. The top rectification section uses structured sheet metal for capillary liquid film spreading to minimize pressure drop. The bottom stripping section utilizes movable valve trays to manage high-velocity gas bubbling, withstanding intense vapor thrust from the reboiler. Multi-component conservation laws govern the core of the system. Mass balance, equilibrium relationships, summation of fractions, and heat-energy conservation are calculated simultaneously. This nonlinear solver framework maps millions of discrete fluid interactions across all 180 stages every single second. In the froth zone, physics becomes violent. Gas jetting at velocities of up to 15 meters per second creates a Reynolds number exceeding 40,000. This intentional chaos shears liquid into billions of microdroplets, maximizing the surface area required for effective chemical separation. These towers must defend against immense structural forces. They face internal expansion hoop stress and external bending moments from high-velocity winds acting on the 85-meter cantilever beam. The calculated safety margin of 26 megapascals is the only physical barrier preventing catastrophic buckling of the steel hull. Dynamic feedback loops are constant. A sudden thermal spike in the steam feed can disrupt the base equilibrium, causing an instant vapor surge. If this surges up the tower and clashes against the massive reflux flow, it threatens to contaminate downstream production lines within seconds. We tame these systems with a real-time digital twin. By using model predictive control with a 1-second sampling rate, the system can detect anomalies and adjust control valves up to 20 minutes before a human operator could even perceive a deviation. Manufacturing these giants requires absolute, zero-defect precision. The hull is constructed from massive carbon steel plates, joined by multi-pass submerged arc welds. Every millimeter of weld undergoes rigorous X-ray inspection, as even a microscopic gas pocket could lead to failure under the immense operational load. Commissioning requires anchoring a 1,000-ton monolith. This involves a deep pile foundation extending 30 meters into the bedrock, using 1,200 cubic meters of concrete. Hundreds of pre-tensioned high-strength anchor bolts, torqued to 4,500 Newton meters, secure the base to handle the massive wind loads. When models break, the result is the nightmare of column flooding. If vapor rates are pushed too high, liquid can back up tray to tray, leading to a runaway blowout. This can cause millions of dollars in damage to downstream equipment, such as compressors.
To improve efficiency, we use generative design to script flawless internal geometries. By linking parametric Python APIs to multi-phase CFD solvers, we can test thousands of mutations. This approach eliminates low-flow dead zones and has successfully increased throughput capacity by 22%.
This is the multi-layered triumph of modern process engineering. By mastering everything from thermodynamics to AI-driven digital twins, we transform high-risk industrial behemoths into predictable assets. The result is a 22% efficiency gain and a 94% reduction in unplanned downtime.